Oi, pessoal. Então, vamos começar um Seminário de Coisas Legais, o primeiro oficial desse ano, né? E, pela primeira vez, vai ser um seminário em inglês. O Stan, ele me falou que para chamar ele de Stan, porque eu não sei pronunciar o nome dele. Ele é polonês, então, melhor fazer em inglês do que em polonês, porque fica um pouco mais fácil, né? A gente está gravando no YouTube, depois a gente vê se a gente consegue colocar legenda também. Para quem não entender inglês, a gente vê se consegue fazer legenda em português. Tá bom? So, Stan, the floor is yours. Thank you very much for coming.
Yeah. Oh. Thank you very much, Marina, for such nice introduction. It's okay if I use this? Yeah, yeah. So that should be switched off. I'm very grateful for this invitation because this is very exciting to be invited for such colloquium. Open colloquium for so broad audience, for all the types of students, all disciplines, and so on. Thank you very much. I would like to thank Sidinia for the invitation to be here so many times already. So this room is not is very well known for me. So thank you. Something stopped. Oh, yeah. So I would like to present you something of the origin of it is in nanomedicine. It was some investigations in nanomedicine. You know, nanotechnology is now very helpful for certain branches of practical science, not only theoretical science. So this came from there. It looks basic, you know. Spherical world, in some sense, people believe that this is spherical, that interactions are spherical. On the subatomic level, interactions are spherical. Sphere is a circumference of the ball, you know this. And sphere was so taught as a so perfect object that, for example, Pascal taught that that's a God. God is a sphere, of the center is everywhere, but circumference nowhere. You understand? So a kind of interesting belief, because something like such quality like God should be so perfect, most perfect. But also in Pythagoras' beliefs, there was a harmony of spheres, you know, as a fundamental structure of the universe. So the sphere, let's be with sphere today. The same radius sphere for first time. So then I show you so spheres might be packed in some way. And last Fields medal was just for packing spheres but in dimension 8. But this is packing spheres in dimension 3. But it's not. I will not present any proofs because there's not much time. That's okay. So you see, the 3 spheres are packed tightly in this way. It's like ball, like in cannons they put these balls like that. And if I add the balls here, then now, for example, here, then there is another one, and so on. You see. This is a process. A slow process, it depends on my move of finger. And gives you something what is called linear, if we consider only the centers of the sphere, we have so-called tetrahelix or something like that. And then this is the chain, you know, very linear chain. Of course, you might not be like that, but I added spheres tightly in such way. Of course, I can also pack spheres in different way, use the minimal energy or greatest energy. So then, you see, if we have greatest energy, for example, then if I add spheres, then we get something like that. So we get some cluster, you see, and they are packed in some way, some optimal way. So the program here is choosing such optimal way, but you see there are holes between them. It's impossible to pack spheres tightly, completely, without any holes and so on, because I explain in a moment, because of size of the spheres. But these are spheres of the same radius. And then, of course, you can find here, if you consider, for example, 9 spheres, then you have something what Newton and Gregory were in quarrel. How Newton was right as usual. So this does that case, and my keys, but they are not tightly attached to themselves. You see, there are some frustrations. If they want to be tightly attached, then they have problem, like people, you know, decide here or here or here. It's very interesting. Okay, so that's what I wanted to show in the beginning. Then some presentation. Now we will forget or replace sphere by its center. Now it will be some more mathematics. Replaced by the center. So, for example, this previous way is if you have this guy here, then if you replace balls by centers, then you have tetrahedron, regular tetrahedron. Yeah, you see this. Okay, so then just go. Of course, I have many programs, but that's not the case to show it anything. So that's presentation. And then, then if you consider such packing, which gives this, oh, it's okay. Ah, no, not yet. Ah, yes, okay. If you have such packings which gives you the clusters, then of course this is something complicated. You know, so after some time appear some holes, and thus it is there. And then if we might have packings which give chains. These are very special packing, but all possible forms are possible to get. In fact, I show you this. If you consider chains, you know, chain is something like that you have these 3 balls, and that the 4th one is here, and so on and so on. That is giving such. Here is linear, but I show you, of course, non-linear. I mean, not so, and then you get a chain, and it appears that they never close. It is something never close. So then you can get every form by this. If they close sometimes, then of course the word. This is why maybe there's variety of forms for life is necessary, is because of the gap, so-called Pythagoras gap, which I show you in the moment. So, so this is just replacement. You see here, replacement of the centers of spheres by the centers and joining the centers, and then we have the such complex, yeah, made of simplexes, but that's mathematical. This is not necessary, and this is just that. Then, and then if I continue this, I get, you see, this one is the same. This is the same. Seems to me the same, but maybe different, but gives the same. But it's easy. This one may be even easier to see. I have, of course, program. You might play with them, but if the not perhaps no time. But you see this gap here. It's almost ring, but it never close. Never close. This gap is maybe very tiny, but there is. And of course, there is a question. What forms we can get by this type of chains? Are they of course, we are not using to infinite, infinite sequence of choices, because we are in our activity finite, so unfortunately. And so usually we consider periodicity. So we have some period and then repeat, and we see that how it is going to infinity. So this is just the ring. What kind of forms? Many forms, but also these fundamental forms which are used in biology. So how to describe such structure? You think this is just picture? No, not exactly. You see, if you look closely to the chain, you see that it has such units, such particles from which he's built up. I mean, this is, you see, if you take three tetrahedrons, all three tetrahedrons are the same. Yeah, because this is just something like that. Unfortunately, I didn't find a toy, magnetic toy to bring you here, but that's maybe. So you see these three the same, but the gray one are the same. This isometric, always isometric. You can put one on another one. But if you add fourth one, this is green, yellow, and red, they are not isometric. They are completely different. You cannot take this and put isometrically, just combine, move for that, for another one. So from such units, three units, such chain is built. But on the first side, you didn't see it. Because there's just this, but it has something like that hidden in the structure. Okay, so that means that using three characters, because you know this is D, F is a flat. You see, because flat is because this, and then we, in some sense, the centers of on the plane. The centers of the tetrahedrons are on the plane. Here, the centers of the tetrahedrons are not on the plane. So this is, say, down, up, and F. Doesn't matter of characters, but at least three units from which we build all this complicated structure. Our alphabet is a bit more bigger, but alphabet of DNA not so big. Has apparently 4. But also in here we can build something with 4. But there's another application. So be aware of that thing. So I show this a bit more. So then this is this 3, and then you add from one hand side and from other hand side this four tetrahedrons build these units. Oh, this one is this flat. And of course, this is FF. If you write FF, that means that you go from first, second, fourth is F, and then omit the first one, and again have 4, you have F next to F. And this way you build the word, which is saying how to read such sequence. And then, of course, on computer is very easy than everything, but not so easy because I show how to calculate everything, but that's later. But of course, this is, yeah. So no, for example, here, such word gives you such shape. And it's easy to read this because you start from the first one and then to the fourth one is U, and then you forget the first one, and then starting from the second one, and you get D. And so on and so on and so on. And these units, of course, in the chain, they overlap partially by themselves, but doesn't matter. But it's uniquely define the shape. Okay, it's beautiful. This is coding something which is on the first sight invisible. Okay. Then, of course, you see, this guy is like that. Such. If you say, do this something, then you get this ring. Yeah, sometimes we just, yeah. And then And then how it is done, like that. How we do this? You see, you take tetrahedron and you reflect it in the face. This is the process by reflection. Reflection is involution. It's fundamental in mathematics in the real world. If you go to the mirror and you see your face on the other side, it's involution, it's reflection. But this is, if you are in atomic level, you have C-star algebras, and star is involution. In quantum physics, even much more involutions are important than in such physics like classical, or almost classical. So then, but involution is a reflection. But I'm happy physicists are here, so then you understand. So, and you see, this is the process. Like in, growing up, the particles is like that. And then, of course, here, you see this structure is here. Yeah, if there are questions. Oh, this one is almost invisible. Where is the gap? Oh, that's, on the first side, it's impossible to find the gap, but there is a gap, of course, because it's impossible that it's closed. It's a few proofs of that fact. Or that chains never close, never locked, never closing. Also, there are also such chains which are based on one vertex. And it appears that 6 of them is this only, and they are very important because they are in some sense minimal. In biology, it's a problem of protein waving. So there's a protein, you know what is protein, and then it takes some form which is optimal in some sense. Waves, and that are most optimal waving here. But of course, if you want to look on that as a protein, then it's necessary to have in mind some different picture, but that's okay. So this is like that. Oh, this is another one. Another one. Oh, you see, it's some time. Well, what is time? We don't know what is time. Time might be just reflection. Yeah, you see, and you might have immediately question: what happens if in these pictures usually these chains they don't intersect themselves? Of course, it's much easier to do such classification where they self-intersect. So the program which calculates all not in self-intersecting is done, but this is relatively complicated and no total. To some big length, but not. We have no program which is totally defining all not in self-intersecting chains. This one is, of course, some spiral. And these examples also and shapes are just to make it for you in some sense easy. There are different shapes, you see, and then a random choice, because this is also very important. There is some randomness here, because if you reflect tetrahedron, then you have 3 possibilities, 3 faces. One you choose, and this choice is random. And this is very interesting because these are kind of random graphs, random chains. That's another story. I have no time to talk about that. Yeah, and dual chains. Duals are just chains. They are maybe also nice because if you join centers of the faces, you get also tetrahedron, because tetrahedron is dual to itself. But if you now consider a chain, then they attach by vertices, because vertex now is a side. How to maybe that's perhaps trivial, but if you have this tetrahedron, then you join the centers of the faces. That's this, that may be not this, and this, and this. You see, then if you reflect the tetrahedron in this big face, then this point is constant. That means that this is just attached like here. And then this Pythagoras gap is looking like that. This has some meaning, these dual graphs, dual. And yeah, dual chains. Oh yeah, they are moving it also in some nice way. That's, you see, why I say about that? Because this is a kind of internal part, central internal part of the tetrahedron. In this case, it's also tetrahedron. But if you consider deformed sphere, then something inside, deformed center, is very important for coagulation. And that's what I presented on this, partially on the conference. Yeah, so, yeah, that's still this Pythagoras guy. But, you know, Pythagoras here perhaps did not know about that. But, closed chains. You see, this coming to, and no possible more, because then they just might intersect. Each possibility is impossible. I mean, it's 3 possibilities, 3 closed. And then icoclusters. Icoclusters, they are this one on this, and this is this just a graph, and this is, as you see, 6 of these, and there's graphs, and then if you try to classify the forms, geometrical forms are very important, because that drag, for example, depends on the properties of drag, depends on the geometrical structure of the protein. Then you see the such generated program. And then if you consider the situation globally, you have kind of situation, if you join the centers, you have the kind of tree of life. I mean, tree of life is here because how we can imagine looks tree of life. Like that. Everybody has its own imagination. So then you see, this is just, if you have this tetrahedron, then you have this isogonal, this one, and also this one. Impossible to draw this. But anyway, you see, if it's more dense, then there are some kind of dodecahedrons appear, but not exact dodecahedrons. This is very exciting thing for me, because on that thing I realized all ways, all chains. So chain is a way on this tree. You see, that what is shorter, that's easy to see. You see, this is the face, and of course, that should be the same length. And also, it's important that the angles between are the same. Okay, this is something here more deep. Okay, now I pass to some shortly, but yeah, just what maybe this is also working now. No. Okay. Very quickly go through this packing stuff. This is the packing problems. You know, square packing. This depends. If you ask how they are effective, the packing, so how much space they cover, like the last Fields medal. This such packing. This is the Barrow Boys packing. Sell as oranges on the market, you know. There's many types of packing, and they are different in sense, and the problems in mathematics were a long time. This is just hexagonal packing. It's different. This packing is connected for physicists also with crystals and so on, with forms, with basic crystal forms. And then this one is the more basic packing. This one, that's what I wanted to say. I don't know if students know that dodecahedron, icosahedron has such property that distance between vertices, distance between vertices is A, is 5% longer than distance of vertex to the center. This is fundamental thing. If it would be the same, maybe life wouldn't exist. Because people, of course, if we covered with the space, we have some coverage of the space, because it's Euclidean space. Then, of course, we might do this, that this is equal in some way. But no, our Euclidean space is Euclidean. Locally, absolutely, but locally is everything organized. So because of that, there are quasicrystals, many things, and a variety of forms. This is, of course, might not be true in some sense, but at least for first sight, but this is very important. When I packed these spheres, it was never closed because of that. I think the students should be taught that just on the first course. I'm not happy that my university, they don't teach this. So, and then, of course, I repeat that on, for example, these forms, this form, or this is, you see this gap, this one, just quickly repeat. Now but maybe before this, I brought something, I brought something to show you, maybe to present to somebody who came here first time. Dodecahedral and icosahedral are dual, each to other. So I have some creation of three-dimensional object from two-dimensional parts. So I have, you see, some plane objects, I put like that. And what I do, only one kind of elastic stuff I take. I am sitting, this fine also, but because this is commercial of my center, then it's easy for me to have it. So I do something. This is kind of thing, you see, and I put two-dimensional things. But to pass to the higher dimension, what I need, you think, of course, this wire, but in general, symbolically, we can say that we need knowledge. If we have in some space which is n-dimensional objects, to pass to the higher dimensional, we have to have knowledge. And this knowledge is this one geodesic here. And if I say, let's be Pythagoras universe, you see, this is dodecahedral. Well, it's created in this way, in 3 dimensions. Maybe I have for you also. If someone wants very much, I have another one. But of course, this is possible to make many things with that. Okay, so then quick presentation of a kind of basic mathematics. So this is, P1, these are vertices of tetrahedron. You see, four vertices. And opposite sides, S1 to S4. So then, this is maybe for mathematicians no problem, for physicists also, but for other. So of course, the distances, of vertices are the same because it's a regular tetrahedra. And then we consider the space, which is a tensor product of this space, 3-dimensional space, and 4-dimensional space of parameters. It is called barycentric coordinates. We introduce barycentric coordinates in this way. Of course, we can look on the tetrahedron in 3 dimensions, like it is. But it's not effective so much. It's more complicated, but it's just, you can, show this, that you should study mathematics, tensor products and other things, different spaces. This is why I prefer this than usual lines and planes. Okay, then you have this tensor product, and elements of these tensor products are just tetrahedrons. So, of course, there is this, for these parameters, this important plane for barycentric coordinates. And then, of course, one tetrahedron is such element, no element of the tensor product, sum of pi and ai star. Star means that this is the form, that this is mapping. This is not the line, not the space, but there's mapping. Okay. But you have, because, so then, of course, how to get a full tetrahedron? Just apply all points of this parameter space, and you get a just combination of this alpha I, pi. That's very simple. And then, if you consider the reflection is in this configuration, I mean, in this affine space. Our affine space, because affine, I say, because I don't know where is the center of this space. Everywhere I can put the center and Euclidean coordinates. So then I take reflection, and reflection is just V into V, this space into V, you know, a mirror reflecting. And then this is a simple mathematics, and then I get, this is this reflection also written here. If you have this point P in the space, then reflection in the phase I is given by, this is also the common formula, very simple formulas, you see? And then if you use this Ri reflection sequence many times, then you get the chain. And then, then the first T is fixed, and then T reflected by A1, and consequently this one, I think that maybe, this is the same week. So then you see this second reflection, they are reflection. We call it here twist morphism. And this, what is, just a moment. This is just the matrices which corresponds to reflections. So you look how simple they are. Just very simple rational number, like 2 over 3, 2 over 3, and so on. But you just compose them. And that's a very complicated number sometimes. But still rational numbers. So fortunately, not so bad situation. And then combination of these matrices, normally in tree space would be much more complicated, but in this coordinates, barycentric coordinates is much simpler. This is just because of that, I use this. And then, of course, it looks like that. This transform the vertices, 4 vertices of one tetrahedron to the another one, and so on and so on. And so you see, so this is just F. These units, F, U, D, are given by the determinant of the vectors joining the centers. And there are 3 possibilities. Determinant might be negative, positive, and 0. That's just the case. This is situation. Shape orientation is given by these vectors, which join the centers of the tetrahedrons. Yeah. And this is that one. The different. So F is 0, of course, the determinant. And maybe fewer. So if someone likes combinatorics, so we can forget about geometry here. Consider only combinatorics. So there are some students who likes combinatorics over everything, so they only play with numbers, with the sequences, and so on. So then, of course, you know, if you have normally to have one tetrahedron, some unit U, you need to have 3 numbers. 3 numbers, because first tetrahedron is done, and then you have one of the faces of this tetrahedron is one number, później another one of the faces of the second tetrahedron, and one of the faces of the third tetrahedron. So there are 3 numbers chosen from 4 numbers, because there is four sides of the tetrahedron, of course. But only 3 are used in reflection, in getting one dead. Then, so for example, if you have such word, then it is such sequence of the triplets of numbers. So the admissible triplets, they have such properties. So that's not so complicated. This is pure combinatorics, very easy to understand. So for students, even maybe exercise. And then, of course, such thing is given like that. And this one is given like that. Oh, and then we can, in this combinatorics, classify all admissible triplets. You see, they are all classify all admissible triplets. 12 for each UDF. But if we reflect, we change the orientation. And that also is important, and then is taken soon. And then this is classification. Yeah, well, maybe this is not so easy. So U chains. If you have only U, then the periodic, periods now needs 4 triplets. One character, U, might be replaced only by 4 triplets. So that's nice, representation, combinatorial representation of these chains. Yeah, that's, then you see. Then maybe I forget, I postpone this because these are just some tetrahedral group, and they use this group and so on. Maybe I postpone this. Oh, this is the tetrahedral group which appear naturally here. There are just relations defining groups, symmetric groups. So this is abstract tetrahedral group here. And this is geometric proper tetrahedral chains. If you have the length here n, then we have this length 3, 4 is 3, yeah, and so on. So you see, we have in this table we have length 13 tetrahedrons. This is a number of proper chains. Proper, not self-intersecting. Not self-intersecting. Well, a bit more, but not so far. Then branching order, B, is usually maximally 3, because you can choose one of the faces. And this is just also characterized by these formulas. And then, this is 0 branching order, and then proper chains sharing one icoclusters described by the smallest unit. You cannot go anywhere and from that cluster folding. And it was used, this is on the base of nanomedicine investigations, where there was some plant and some powder of particles, spherical particles, of droplets, kind of droplets in the beginning, which has 3 types of molecules. And there's a silica molecules, which smallest one, and built the something what you see. And that was in collaboration, Polish-Japanese collaboration of chemical engineering. But mathematics was crucial here. If no mathematics, they never get something what I showed. This one they got, but they never would got this one. But that is fundamental. These are spheres with holes. So if you have such spheres with holes, you can put drag there and inject and go magnetically, for example, to the sick place. And, normally, if you have an injection, you have everywhere this drug. But here, no. So that was very, very successful. and then that is already used in sold in, I don't know, maybe not in Brazil, but certain states, because we saw this this company to United States. So I don't know. I was not deciding because I was only one of the people who made this that this was, but they didn't follow me anyway. So you see, but this is working for LAN. It's very good because then they can remove this material, because the problem is that from blood still they try to find a method how to remove the these particles. These are nanoparticles. So anyway, this is always danger that they may coagulate somewhere and stop the blood flowing. So this is but for LAN is perfect acting, because they go to the smallest places where the LAN are sick. So this is important. Of course, now they ask me to do this hybrid, so then 2 or 3, but I know if they say again to someone, then I don't work. So that is just, that's maybe as a bigger one than you can see, but yeah. And that problem here was that this is stable, that's a sphere. Normally they got kind of pieces of material, not spheres, some shells or something. So that was the achievement. And then, yeah, some, that's also, this is used to write, to code in DNA sequences, but that's another story. This is this model for chains, and and we checked also, is this here, but you know that in tetrahedron there is 4 vertices, so it's possible also to use vertices, not only UDU. That's you know, if you do something like that, you check everything if it is working, you know. So then this is 4, but and then we have this possible coding of some short DNA. So that's it. Thank you very much for your attention. Really, I'm very excited that you looked on this stuff. Thank you. Yeah. So I'm okay, yeah?
Thank you, Stan. This is the certificate for the talk. We always give the orange certificate.
For the talk.
Yeah, it's the certificate. You have to put it somewhere to show the university that you presented here. Alguém tem alguma pergunta, algum comentário? Se quiser perguntar em português, eu traduzo, se for o caso. Não? Então, todo mundo com vergonha? Yeah. Let me give you the microphone.
Just like this. So I just wonder whether to prove that the chains always has a gap, if perhaps a method would be to prove that certain discrete dynamical system or composition of them has no periodic point.
You are close, perhaps, but but already 2 proofs. One proof is old one. I mean, not very old, but in 80s, I think. The another one is he gave us our friend Ian Stewart recently, because I not recently, some years ago, because I showed him and asked him for another proof. He proved. But this is, you know, if they are closed, then these matrices, and then they have, you know, you can just, if you apply some vector, then you get the same vector in this way. So
I'm close.
You are close. You are very close. But these proofs are a bit. One is very algebraic. This one by Yen is semi-groups technique, where we show that the semi-groups are just not never, they are finite or something, and then this is another proof. But this is this is very important here that they are not close there. Maybe some proof, another proof also would be nice to have.
Okay.
So
Thank you.
if we think about that, if you think that, thank you.
Mais perguntas?
Oh.
Hello. It's not a question, but I just like to say that I find very beautiful to see science talking to each other. Like here we have math, biology, chemistry, and a lot more. And I'm very happy to see this.
Thank you.
Thank you.
Thank you for this words, of course. But yeah, thank you.
Perguntas, comentários? Não? Então, muito obrigada. Thank you, Ian.
Thank you, Marina, for this. For you. You organized this, yeah? That's not easy. Thank you.
Ó, a gente ainda não tem próximo marcado, então se alguém tiver interesse de apresentar, é só falar comigo. Beleza? A gente vai avisando quando aparecer.